So suppose that we want to find out the possible eigenvalues and the energy eigenvalues and the energy eigenfunctions for some given potential. So there are two aspects to this problem. The first one is that we have to propose an energy, and second is that we have to propose a trial wave function. So given all the general comments that we've been making so far, let's see how we can use those general observations to figure out the ground state wave function for a finite potential well. Of course, this is something that we know the answer to. So this will be to kind of test how our general observations can be used to figure out something that we already know. Later we will discuss examples that we do not know the answers to. So remember that in region 1, the solution will be a sinusoid, but that the energy of the energy will determine the curvature of the sinusoid. So the more higher energy it has, the more curved our sinusoid will be, and the less energy it has, it'll be less curved. But of course, which sinusoid it'll be will be determined by whether or not that curve matches continuously to the exponentially decaying wave function that we'll have in region 1. So in region 1 and in region 2, if we have a wave function here, another wave function here, we have to make sure that over here both psi and psi prime are continuous. Let's try to figure out the energy and the wave function. So this is our potential. So it's the finite potential well. And let's just take 4 energy values. So this is a EA, this is EB, and this is EC, and this is ED. So, and then let's sketch the wave functions. So let's sketch the first wave function, the wave function for EA. So EA is quite high as an energy, and therefore the wave function in region 1 will have quite a bit of curvature. It'll have so much curvature that it'll hit the x-axis somewhere inside region 1, and of course once it hits the x-axis it'll curve towards the x-axis again. But by the time it goes into region 1, it's in the negative part, and therefore what will happen is that it'll then curve away. Sorry, I keep erasing it. It'll curve away, and therefore we see that we are going to get a wave function in region 2 which is exponentially increasing. So this cannot be the right wave function, and therefore we cannot accept EA as the correct energy eigenvalue. What about EB? So EB is less than EA, but it doesn't go to 0 before entering region 2. But once it does, it tries to go to 0. It curves away from the x-axis, but when it hits the x-axis, its first derivative is not 0 over here. Although the wave function psi is 0, its first derivative is not 0. And therefore, as it crosses the x-axis, it will move away from the x-axis. It'll curve away from the x-axis, and therefore this wave function is also going to give us something which is exponentially blowing up in region 2. So then we decide that psi b is also a wave function which is not acceptable, and therefore EB is not an acceptable eigenvalue. Now let's take, so the energy EC, let's see what EC is. EC is the lowest energy we have, and because it has lowest energy, the wave function has very little curvature in region 1. So in region 1, it'll be something like this. Sorry. In region 1, it'll be something like this. But as it enters region 2, it never reaches the x-axis. It just curves away from the x-axis, and therefore we see that this also is exponentially blowing up in region 2, and therefore psi c is also not an acceptable wave function. So this is not an acceptable energy. ED, on the other hand, has exactly the right value, such that it looks very similar to this wave function, but the good thing about it is that as it enters region 2, it tries to move away from the x-axis, but when it hits the x-axis, its first derivative, psi 1, is 0 at this point, and similarly at this point. And therefore, we can just, it doesn't have to, curve away from the x-axis anymore. So this is an example of a wave function, which is acceptable. So psi of d is the acceptable wave function, and therefore this is the acceptable energy eigenvalue. Another observation that we have is that the sinusoid which fits our potential, which is this one, would be a sinusoid for which the infinite potential well will have larger width. So if I take like our sinusoid and I analytically extend it beyond, then we see that this is going to be that if we were to take an infinite potential well, its width would be greater than the potential well that we are dealing with. And therefore, if I look at the ground state energy of an infinite potential well which has the same width as this thing, that would have a higher energy. So the ground state energy of a finite potential well of this width will have less energy than the ground state energy of an infinite potential well which has the same width. Now that we have discussed the ground state wave function, let's look at the higher, one of the higher excited states. So we know that if you had an infinitely deep potential well, so if this was going up all the way to infinity, then the first excited state will have something like this. Whereas if instead it's a finite potential well, then we will have something of this form. So another important observation is that the nth energy state of a one-dimensional, so the nth energy state of the one-dimensional bounded potential has n plus 1 zeros, including the zeros at plus and minus infinity. So what do I mean by that? So look, take this guy. So this corresponds to the energy state n equals to 1. And how many zeros does it have? Well, it has no zeros here. It has a zero at infinity here, and at infinity here. Of course, this goes to zero very rapidly. You don't have to go all the way to infinity, but in principle, an exponentially decaying solution only goes to 0 at infinity. So n equals to 1 state has n plus 1, that is 2 zeros. Whereas the first excited state, which is n equals to 1, that has how many zeros? It has 3 zeros. So n equals to 1 has, so this should be n equals to 2, of course. So n equals to 2 has 3 zeros. So this is a general feature of bounded potential that we have to keep in mind. It's actually a theorem, and it is independent of the form of the potential. So this is valid for all one-dimensional bounded potential.